Okay, hello. In this bunch of videos for differentiation and integration, I'm more or less just going to run through a lot of derivatives and a lot of integrals. So actually, most of these questions actually come from the December holidays package, that was given out at the end of C1 for differentiation and integration. So I'm just going to go through more or less. I won't go through every integral or every derivative, but I'll just try to run through and see if we can get over some fundamental integration and differentiation techniques. Okay, so this is going to be part one. I'm going to do a bunch of integrals now. So our first integral for this video is as follows. And as you copy the integral down, you can already start thinking about how you are going to integrate this. Okay, now obviously, because on top is actually a linear term, and on the bottom is actually a quadratic term, this means that I'm going to have to use partial fractions. So how do I split this particular integral up into partial fractions? What I'm going to do, okay, is because I have 7 plus x on top, right? So I know that my this fraction, okay, is going to be equals to a over one of my linear factors plus b over the other one of my linear factors. And now this a and this b is going to be some kind of integer, but we don't know what integer this is yet. But we know by cross multiplication that a times like that, right? Cross multiply like that. So a times 2 plus x plus b times 1 minus 2x will give you what's on top here, right? 7 minus x. That's basic plus x, sorry. So that's basically how you do your partial fractions. So if you expand this, you will get 2a plus ax plus b minus 2bx is equals to 7 plus x. And then what you're going to want to do is you're going to want to group all the terms with x together and then group all the terms that don't have x. And then you can do by comparison. So by comparison, if I compare this, the terms with x, I will have a minus 2b. The coefficient of x is 1. Okay, and then comparing the terms independent of x, I get 2a plus b equals to 7. So if you solve these two simultaneous equations, which by the way you can press your GC and SC2, you are going to be able to get a is equals to 3 and b is equals to 1. So you can take your time, pause the video now, and take a look at your GC or SC to check that you get this. Okay, so let's go back. We can express this as 3 over 1 minus 2x dx plus 1 over 2 minus x dx. So because I have split it now into two integrals, do you notice that both of these can actually be integrated using the standard ln forms? So if I want to make my life even easier, I will make the numerator here 1. Okay, this one, the numerator is already 1. And then basically this is just going to be, my coefficient of x here is minus 2. So when integration, I always need to take the reciprocal. Okay, and then ln, remember your modular sign. In some of the formulae for integration, and also in the standard integrals given in MF27, you will actually not be shown the modular sign for these terms. It will actually be shown as square brackets. But please just know that you should write it as a modular sign in exams, okay? Because you don't know whether this is positive or negative, so you need to write the modulus. And then this one is just simply ln mod 2 minus x. And then now there are no more integrals, so don't forget your plus c. And I'm just going to simplify now the coefficients here. So that will be minus 3 over 2 ln mod 1 minus 2x plus ln mod 2 minus x plus c. So that's it for our first integral of this video. Okay, now next integral we've had some standard forms already. Before I move on, let's do another one that has standard forms. Okay, so I'm now going to do this particular integral. You can copy it down with me, and while we are copying it, just have a bit of a think about how you're going to do this. Okay, so the first thing that you might notice about this particular integral, okay, is that this ex is on top, right? And then on the bottom right, I also have an ex, and of course the derivative of ex is just itself. So can we actually do something about that? The answer is yes. Notice what happens. The pesky thing here is this constant 2. So we're just going to get rid of this, okay? By just taking a half out of here. So I am going to get this. And in general, not only in integration, but also later on in series expansion, it is very useful whenever you have a fraction to get rid of a fraction by simply expressing this as a negative power. So this is going to be minus power half. Okay, and the thing that you notice, right? What is the function that we have in here? The function that we have in here is 1 plus ex. What is going to be the derivative of this function? So let's label this function fx, okay? So if fx is 1 plus ex, then what is going to be f prime x? F prime x is just going to be ex, okay? Let me write that in blue for you. F prime x is ex, and this ex is right here, right? So this is f prime x. So you see that we are getting a very classic case of the standard form. So this is a standard form that you need to know, similar to the standard form for ln and fractions that I showed you earlier. The standard form f prime x times fx raised to a certain power n. N in this case, this power n is just going to be equals to minus half. So I am going to, the standard form says that this is going to be equals to fx power n plus 1 over n plus 1 plus c. So let's just follow this standard form now, and we are going to get, once again, I have my constant outside, and then I worry about the thing inside the integral. So my n is minus half, right? So I want n plus 1, so I write half. And then my denominator is going to also be over half plus c. So therefore, obviously this half and this half is going to cancel. So I will simply get, in this case, it's up to you if you want to leave it as a power half, but I personally prefer to tidy things up as far as possible and write a root plus c. Okay, that is it for these two integrals. So so far I've showed you a lot of standard forms. Next, I am going to take you through some integration by parts. Okay, so for our first integral by parts today, we are going to look at an integral that looks like this. Okay, now remember when you are integrating by parts, okay, what's the order for integrating by parts? L-I-A-T-E. Okay, and when you have L-I-A-T-E, the reason why this is the priority order for choosing what is the function u and what is the function v is because this is actually the order of functions that are from the most difficult to integrate all the way to the easiest to integrate. Because my formula for integrating by parts, okay, there are different variations of the formula, but the way that I prefer to remember it, I write it like this. Where dv means uh means d, like the derivative of v, so this is the derivative of v, then of course is going to be with respect to x lah, because u and v are both functions of x. And then after that, du is just the derivative of this function u, and of course this will be with respect to x. So I know some, in fact a lot of formulae will write it in terms of things like u prime or v prime, but I just personally prefer not to do that. Okay, yeah, it's just my personal preference. I prefer to remember the formula like this. But the general gist of it, okay, is that when you go from u to du, this is a differentiation. When you go from dv to v, this is an integration. So v is the function that you are going to want to integrate because it can be integrated. U, on the other hand, is the function that you would much rather differentiate than integrate, because u, by nature of the function, is a lot harder to integrate than v. So that's why this is my priority order for picking u, L-I-A-T-E. Okay? So in this case, what is going to be my u and what is going to be my v? So in this case, remember I have an inverse trig here, and then I have a exponential here. So obviously I'm going to want to make my inverse trig function be u. So this is u, and then this will be v prime, or I will annotate it as dv, but it's basically the derivative of the function v. Okay, so if u is sine inverse of ex, then u prime is just going to be, we are given in MF27 the way to integrate, or rather the way to differentiate all the inverse trig functions, and based on MF27, the derivative of sine inverse ex is going to be as follows. So just remember, this is a differentiation, okay? I do not integrate the function u, I only differentiate the function u. If you want, you can write this part as e power 2x, but I prefer to keep it like that. Okay, so if dv or v prime is ex, then v is just going to be, I integrate ex lah. And what's the integral of ex? Ex. See, it's nice and simple. So I'm going to move these two pieces of information down here, and I'm going to get to integrating. So I'm going to express it in this form now. Okay, I'm going to express it in this form, and I'm going to begin writing. So this is going to be equals to so u v, or in this case I'm going to write it in the other way. So this is my v now, and this is u. So I have integrated v already, I've taken care of v. I haven't dealt with u yet, I haven't differentiated u. So please remember that this is a minus sign, please don't write it as plus, times ex, which is my v. Now I'm going to take care of u. So this is going to be ex over root of, fine, I'll write it as e power 2x. And this entire thing with respect to x. Okay? And then now the difficulty arises. How exactly do we integrate this monstrosity of a thing? Let's see, okay? So everything here is settled already, right? So let's not worry about it. Let's just copy it over first, and then we can think later. Actually, I think the bracket is optional lah. No, I'll put the bracket, it's nicer that way. So now we are going to try to integrate this monstrosity of a thing. Okay, now because I have ex here and ex here, first thing I'm going to do is I'm going to combine it. Okay, and I'm going to make this e power 2x over 1 minus e power 2x. So what do you notice? What does this integral look really like? The integral that we just did earlier, right, up here, is exactly the same. Oh, well, almost exactly the same. But in this case, instead of ex, I have an e power 2x. So we are just going to do the exact same thing. I don't think I need to talk you through this, right? We literally just did it. So this will be I'm going to express it as minus half dx, and so this is going to be this is minus here and minus here, so this will be a plus. So I have my fx, f prime x, use the standard form. Oops, I meant to write it in black, sorry. Okay, 1 minus 2 e2x n plus 1. So half minus half plus 1 is half. And then over here, half plus c. So that is going to be something divided by half is just 2, right? So it's just going to be ex sine inverse ex plus 2 roots plus c. Okay? So you will integrate this like that, and then you just use the standard form f x n plus 1 over n plus 1. Okay, that's how you get this. Can? So, one more example of integration by parts for you. This time, how about we do a definite integral? Okay, for fun. So, a common mistake when you are applying integration by parts to a definite integral is you might, because a lot of people, when they first learn integration by parts, they may not be exactly familiar with how to apply it to upper and lower bounds. So a common mistake, right, which I have actually done before as well, is to try and treat it like an indefinite integral first, then only sub in the bounds. It's technically possible, it's technically mathematically correct, but it's not very elegant. So how you are going to do it, I will show you now, okay? Let us also use this opportunity to revise a bit of our trigonometry. Okay, so our integral that I'm about to show you is as follows. So first thing to do, as with any integral that you need to integrate by parts, is you use LIATE to identify what is my u and what is my v, okay? So in this case, my u is obviously going to be this logarithmic term. This is the one that I want to differentiate. I don't want to integrate. So if u is ln of sine x, the derivative of u is going to be one over sine x times d dx sine x. So that's just cos x over sine x, and cos x over sine x is just cot x, cotangent x. Okay, and then so this is my u, which means that this is my dv or v prime. So if this is cos x, then v is just going to be the integral of cos x, which is sine, yeah, integral of sine of cos x is sine x. So you differentiate sine x, you get cos. You differentiate cos, you get minus sine. Then it's the other way around for integration. You integrate sine, you get negative cos. You integrate cos, you get positive sine. Okay? So please don't confuse all this basic stuff that you learn in Sec 4 E-Math, okay? So let's get down to it. Now, usually, if this were an indefinite integral, I would simply write this is equals to u is ln sine x v is sine x, and then I would go on to minus my integral, right? But because this is a definite integral, in front of this thing, okay, I'm going to already insert my square bracket, and then insert my bounds. So remember how to do definite integration. And then in this integral, because it's a definite integral, I'm still going to write my bounds. Okay, so please don't make the mistake of randomly having your bounds disappear. Okay, so actually, let me just not write this as cot x, okay, because it's not necessary. We'll just write this as cos x over sine x. You get how to integrate this to go from here to here, right? Okay, good. So in this case, I want v times du. So v is sine x, and then times cos x over sine x. Yeah, now you see why I didn't want to simplify it, because now 这个跟这个可以 cancel. So I am just left simply with the following. Minus, and now this is perfectly integratable to us, right? So now comes for the very, very tedious and not fun part of definite integration. You need to actually sub things in. So I am not going to show you how to sub in lah. Basically, right, your subbing in of your special trigo values, more or less you just learn in Sec 4 A math already. Okay, but if you, like me, didn't memorize the trigo values table in Sec 4 A math thinking you will never need it, well, what I personally do is I just take my scientific calculator, right? Then I will key in, oh, sine pi over 2, cos pi over 2, sine pi over 4. And then I know that the answer is always some permutation of something root 2, something root 3, something lah. But as you get more and more familiar with all this and you'll be doing a lot of trick in integration, hopefully you will get better and better at recognizing such that you no longer need to memorize. Okay? So please do get better like that. Anyways, somehow by memorizing or otherwise, you will figure out that this simplifies to the following. Okay, why 0? Because sine of pi over 2 and then times ln. Actually, I'm just going to press my scientific calculator with you. Okay, so if you press your scientific calculator, which I can't show you on the iPad, you should be able to get these values. And basically, this is just going to be integrate cos x, you get sine x. And then just sub in lah, sine pi over 2, cos pi over 4. Sine pi over 2 happens to be 1. Oh shit, my calculator is in degrees. That's why. Okay, I'm so sorry. Please don't make the same mistake I just made, okay? I set my calculator to degrees instead of radians. Anyway, so sine pi over 2. Yeah, sine pi over 2, you should get 1 lah, hopefully. And then sine pi over 4 is 1 over root 2. Okay, 1 over root 2 and root 2 over 2 happen to be the same thing. But it's just that for historically unknown reasons, when we are writing the exact value of trig identities, we prefer to write 1 over root 2. Okay? I also have no idea why. It's just the way that things work. So I've spent quite a lot of time on this integral. Let's stop harping and simplify this. And then minus, so sine pi over 2 is 1, sine pi over 4 is 1 over root 2, and we are going to get it. So leave it in exact form, leave all the ln something as just ln something lah, because you can't simplify that. So this thing is going to change to a ln 2, and then plus minus 1. Okay? And just remember your definite integral, I don't need my plus c. And when they say, without using a calculator, determine the exact value, means I must leave all of these all in exact values, okay? Please make sure you do that. And because we get so used to hearing that we have to perform definite integration this way, a lot of people will stupidly go through all this trouble for a 1 or 2 mark question. If the question never say cannot use GC, you can use GC, okay? I trust that you guys know how to solve definite integral using your GC, okay? I don't think I'll do a video on that lah because I will need to get my laptop out and I don't like that. So that is it for integration by parts. Since we are on trigonometry, just a quick one. I will show you a couple more integrals before I get to the end of this video. And then we are going to do more integrals in the next video. Okay, so what's an integral that I can show you? Let's try this one, okay? 1 plus cos 4 theta 1 d theta. Okay, so basically what you're going to need to do is you're going to need to use the double angle formula. So when you are applying the double angle formula, I want to show you something, okay? In your formula booklet, you are going to know, and you know this from Sec 4 A Math already, that the double angle formula in general is as follows for cosine, okay? This is the one that's particularly useful. Now there are three ways that you can write the double angle formula of cosine. And I am sure which way to use in the present context of the question has been a mystery to you since Sec 4 A Math and will continue to be a mystery to you all the way until you sit for your A-levels. Basically, right, you see that I can use this to simplify a lot of things. But typically, for integration purposes in A-level, the two that are most useful for us, okay, are this one and this one. Why? Because cos squared of something in itself is unintegratable. Sine squared of something in itself is also unintegratable. But you see that if I use the double angle formula to simplify, this means that I get 2 cos squared A is equals to cos 2A plus 1. Therefore, cos squared A is this entire thing divided by 2. And now suddenly this is integratable, right? You know how to integrate something like this, right? Yeah, see? And similar case for sine squared A as well. So for sine squared A, 2 sine squared A is just going to be 1 minus, is minus, right? Yeah, minus cos 2A. Therefore, sine squared A is going to be half minus half cos 2A. Once again, this is perfectly integratable to you, right? You know how to integrate this, right? Fantastic. So, if I am able to simplify things like that using the double angle formula, I will be able to actually integrate expressions involving cosine squared and expressions involving sine squared. Okay, I will see if I can find an integral covering this in the next video because this video is getting rather long already. Okay, so let's just do this integral. If I use the double angle formula, in this case I'm given cos 4 theta. Okay, so I can actually express this because it's 4 theta. I will write this as 2 cos squared of 2 theta. Numerator remains the same. And so once again, this constant here is pesky. I'm going to take it out by just taking out half. And 1 over cosine squared is just secant squared. Okay? And please don't be a clown and forget how to integrate secant squared. People, we learned this in Sec 4 A Math. Integral of secant squared is tangent. And remember, because this is a 2 theta, I must take out another half. So this one instead of half will become 1/4 tangent 2 theta plus c. Okay, so this video has been getting a bit long. I think this might end up being a 3-part instead of 2-part series. So I've shown you 5 integrals in the past half hour or so. Thank you very much for being with me and I'll see you in a bit.